So, you ask an AI to book you the cheapest flight to your sister's wedding and drop it on your calendar. Simple, right? Here's the reversal. With nothing built, absolutely nothing happens. No agent, no booking, no calendar entry. Just a prompt sitting there, useless. So you add a language model. Now it picks a flight and forgets the wedding date halfway through searching. Why does something this smart fail at something this basic? Because a chatbot isn't a system, it's a brain with no body. Today we're building the body, layer by layer like an operating system. A kernel, memory, tools, guardrails, all of it. Until this actual task, flight booked, right dates, on budget, on your calendar, actually works. Every failure you're about to watch is a missing layer. Let's build the machine that doesn't fail. Here's the part that trips people up. You'd think the fix for a forgetful agent is just a smarter model, more parameters, more reasoning, problem solved, right? Wrong. The reveal is that smart was never the missing piece, a boundary was. Real agent systems don't let the model touch memory, tools, or the flight API directly. Every single one of those calls gets routed through a kernel layer first, the exact same way your laptop's OS won't let a random program touch the disk without going through a syscall. That's not a metaphor, it's literally how these things get built. Run our wedding flight task on just a raw model, and it still can't hold the date and search and remember your calendar at once because nothing's mediating those calls. It's one brain doing everything with no separation of concerns. The kernel isn't a nice to have, it's the thing that makes agent mean something more than chatbot with extra steps. So the kernel's in place, every call gets mediated. But watch what happens when you hand our task to one single agent doing the whole job. Searching flights, checking your calendar, holding the wedding date, booking, all at once. It stalls. Not crashes, stalls. Because a single agent setup is fine for a one-step task, but the second you need multiple sources coordinated at the same time, one agent juggling everything just runs out of hands. This is where production systems shift to an orchestrator pattern. A main process breaks the objective into steps. Search, then check, then book, and hands each one to a specialist worker instead of forcing one model to do it all. Skip that split and here's what it looks like on the ground. The agent starts the flight search, gets halfway, and never actually gets to opening your calendar at all. Status: stalled. Okay, so we've split the work across an orchestrator and workers, but split labor still needs a shared brain to hold what's already happened, and that's where the next crack shows up. Our workers finish the flight search, but the context window is only so big. Once it fills, the system has to summarize and drop detail to keep going. Guess what gets summarized away? The wedding date, your seat preference, your budget cap, gone, flattened into a vague note. So we split memory into two tiers. Short term, the live context window itself, and long term, a store outside it that holds facts across the whole task. Now the date and your preferences live somewhere the model can't accidentally forget them. Status update. It books, but with no spending cap. No check before it charges your card. So memory is solved. The date, the budget, your seat preference, all locked in long-term storage now. So it should just work, right? Here's the ugly part. It books a flight. Wrong dates aside, wrong card gets charged, and nothing stopped it. No spending cap, no human glancing at it before it fires. That's not a memory problem anymore. That's a missing control plane. Production agent stacks treat this as its own layer, separate from planning and execution entirely. Sandboxing, spending limits, a human checkpoint before anything irreversible happens. A kill switch if it goes sideways. Without it, the agent isn't reckless, it's just unsupervised. It doesn't know $300 is a lot because nobody ever told it that mattered. Run the wedding task now. Dates are right, calendar's right, and it still books first class on your debit card. No confirmation, no one in the loop. That's what happens when capability outruns governance. So governance is bolted on now. Spending caps, a human check before anything irreversible fires. Good. But watch what's still missing. The booking API call just errors out, silently. Nobody's watching the pipes. This is the layer nobody brags about, observability. Every tool call an agent makes needs to leave a trace. Did it fire? How long did it take? Did it succeed or fail? Captured as data, not vibes. Production systems wire this in from day one, the same way you'd never ship a server without logs. Without it, a failed flight booking doesn't look like a failure. It looks like silence. And silence gets mistaken for it's handling it. So we add tracing across every tool call in the chain. Now, run the wedding task. Search fires, calendar checks, booking call errors, and this time something actually notices. The system flags it instead of going quiet. That's the difference between broken and known. Tracing in, we can finally see when something breaks. But here's the next problem. Seeing a failure and stopping a failure are two different things. Right now, if the flight search picks a top tier model to do dead simple triage, just classifying is this a date or a price, it works. It's just brutally expensive to run at scale. Production systems route that differently. Cheap model for triage and classification, mid tier for the actual implementation work, and the expensive model reserved for planning only. Skip that routing, and here's what it looks like on our task. It books the right flight, on budget, dates confirmed, and burns a small fortune doing triage a calculator could have done. That's not a crash, that's money quietly leaking out of a system that technically works. Model routing fixed the money leak. So now everything's cheap, fast, tiered right, but we've still got no idea if any of this is actually working as a system. Here's the gap. Traces tell you a single call failed. They don't tell you the booking worker and the calendar worker are out of sync, or that a coordination handoff between them quietly dropped a step. So we close the loop. Think of it as the full life cycle watching itself. Plan, execute, observe, evaluate, adjust. With execution traces feeding back into what the orchestrator does next, not just sitting in a log nobody reads. That's the difference between monitoring and actually correcting. Run the wedding task now. Search runs, calendar checks, booking fires under budget, and the system watches its own execution end to end. Dates right, budget right, calendar updated. Nothing silent, nothing runaway. The machine finally checks its own work. Alright, so the machine watches itself now, adjusts, corrects. Feels done, right? Except run the wedding task one more time and watch the machine roles themselves. The team building this agent, the team running it in production, the person actually chatting with it. Those are different jobs on different machines, and right now they're tangled into one. Here's what that looks like when it bites. Someone pushes a debug build meant for development straight into the machine that's actually booking your flight. No separation between building, distributing, and running the thing. So a test tweak meant to poke at the calendar worker in isolation goes live, and suddenly the agent booking your real flight is running on code nobody signed off for production. Dates are right, budget's right, but you just shipped a live financial transaction on a debug path. That's not a bug in the agent, that's a missing wall between dev and prod. Okay, so the roles are separated now. Dev machine, hub machine, running machine, all walled off. But separation alone doesn't fix the wall. It just tells you where the wall needs to be. So here's the actual fix. 4 distinct machine roles, each with its own job. One builds and debugs the agent. One distributes it, one just runs it live, and one handles you talking to it. A debug build physically can't reach the running machine anymore because it was never given a door there. Run the wedding task now. The code booking your flight came from the running machine only, nothing borrowed from a dev sandbox. Dates right, budget right, calendar updated. And this time, the path it took to get there is actually the one meant for production. So the machine roles are walled off, production's clean, dev can't touch it. Should be solid now, right? Except run the wedding task one more time and look at what's still missing. Nobody's watching the seams between stages. The plan stage hands off to execution. Execution hands off to observe and adjust. And if one handoff drops a signal, there's no unified trace tying it back to a single incident. Here's what that looks like on the ground. The booking worker finishes, but its success signal never reaches the calendar worker's queue. Both machines report fine individually. Nobody sees the gap between them because monitoring was built stage by stage, not as one closed loop watching itself end to end. Flights booked, calendars untouched, and every dashboard says green. That's the failure mode that looks like success, until your sister asks why it's not on your calendar. So the seams were the problem. One stage says fine, the next stage never hears it. Here's the fix. You stop treating plan, execute, observe, and adjust as separate logs and wire them into one closed loop, where every handoff carries a single trace ID all the way through. The booking worker's success signal doesn't just get logged locally anymore. It has to actually reach the calendar worker tagged as part of the same incident, or the loop itself flags the gap. Think of it like your OS kernel again. Syscalls don't just fire and forget. Something checks the return value. Same principle here. Run the wedding task now. Booking confirms. That confirmation is tied to the same trace as the calendar update. And if the handoff drops, the system catches it before your sister does. Flight booked, dates right, on budget, and finally, actually on your calendar. Alright, the wedding flight book's clean now. One request, one agent, one trace. But that's the easy case. What happens at 1,000 requests a night or a million? The kernel boundary that mediated one booking now has to schedule calls across a whole fleet of them, competing for the same LLM access, the same memory store, the same tool slots. That's not a bigger version of the same problem, it's a scheduling problem. And the machine role split you just wired in, it stops being tidy architecture and becomes survival. Because now you've got separate fleets, machines building agents, machines distributing them, machines actually running bookings, and machines just talking to users, all needing to scale independently. Run 1,000 wedding flight tasks tonight, and the one that fails isn't the booking logic. It's whichever layer you size for one. Let's talk price, because 1,000 requests a night isn't just a scheduling problem, it's a bill. Route everything through your top tier model, and you're paying planning grade costs for work a triage classifier could handle for pennies. That's the whole case for tiered routing. A cheap model for triage and classification, a mid tier model doing the actual implementation, and the expensive one reserved only for planning. On our wedding task, that's the difference between one call burning premium tokens to check is this a date, and a fleet doing the same thing at a fraction of the cost every single night. Skip the tiering and the fleet still books flights correctly. It just quietly costs you 10 times what it should, month over month, for identical output. Same booking, same dates, wildly different invoice. So now you've seen every layer: kernel, memory, orchestration, governance, tracing, tiering, the closed loop, the machine roles. The real question isn't, should I build all this? It's which layers earn their cost for your task. Booking one flight for yourself, single agent, basic memory, a human check before it charges your card. That's enough. You don't need fleet scheduling for a task that runs once. But the second you're running this for 1,000 users a night, the arbitration flips. Orchestration stops being optional the moment you've got parallel sources to coordinate. Tiered routing stops being a nice to have the moment triage volume outpaces planning volume. And the machine role split only pays for itself once dev, distribution, and production genuinely need to scale on different clocks. The criteria is always the same. Match the layer to the failure it actually prevents at your scale, not the scale in a diagram. So how would you actually start building this today, from scratch? Don't build all 9 layers on day one. Build the kernel boundary first. Every LLM call, every memory read, every tool invocation routed through one syscall-style layer. Because that single decision determines whether anything you add later can even be governed or traced. Then add memory tiering before orchestration, not after. Splitting short-term context from a long-term store is cheap to wire in early and brutal to retrofit once workers depend on whatever's in the window. Only once those two exist do you earn the right to add an orchestrator, because coordination without a memory boundary just multiplies the forgetting. For our wedding booking task specifically, kernel plus tiered memory alone gets you a correct working agent. Everything after that, routing, tracing, the closed loop, is what you add once one booking becomes 1,000. So here's the actual next step. Don't design your agent by drawing boxes. Design it by breaking your own task the way we just did. Run it, watch where it stalls, forgets, or overspends, and let that failure tell you which layer to add next. Kernel boundary first, memory tiering second, everything else only when the failure demands it. That's the whole method. Take your own version of Book My Flight, whatever it actually is for you, and run it raw. No agent. See where it breaks. Build one layer. Run it again. That's genuinely how you avoid building 9 layers of infrastructure for a task that only ever needed 2. Alright, your turn. What's the system you want me to take apart next? Drop it in the comments and I'll build it right there with you.